Hello, everyone, and welcome again in your channel, Math Made Easy. Today, we are going to continue with matrices, but today I'm going to show you something quite interesting. Remember, when we were talking about the size of matrices, we didn't mention the following. If I have a matrix that looks like that, A, for example, is, let's pick some easy, 2, 2, okay? And let's pick another matrix, let's say B, and B is a 2 by 2, 3, -1, 2, 4. And I'm going to multiply B times A. B is a 2 by 2, like we said, and this is 2 by 1. And because the inner numbers match, then I can multiply B times A, and the resulting matrix will have 2 rows and 1 column. So it would be also a vector like A. Okay? So now let's do it. 3 times 2 is 6, minus 2 is 4. 2 times 2 is 4, plus 8 is 12. This vector was having a slope of 1. How did I know? XY. XY. I move 2 units to the right, 2 units up. So I have a slope of 45 degrees, meaning a slope of 1. But the resulting matrix has a slope of 1/3. I moved 4, I'm sorry, slope of 3. I moved 4 to the right and 12 up. So the direction of this guy has changed. So it's like this produced some kind of rotation. In fact, this is really a rotation. But we are saying there may exist, in fact, in this case, they will exist, a matrix that if I use it instead of B, let's call it C. If I multiply C by A, I will get a vector that has the same slope as A. So it only dilate it, meaning shrink it or stretch it. It doesn't change its direction. This is very important in many applications. The question we are going to answer today is how to find that matrix. That brings up the topic of eigenvalues and eigenvectors. So what are eigenvalues? We'll see that. In order to find the eigenvalues, what we are going to do, this is matrix B. Okay, we called it B, could have called it A, doesn't matter. Matrix B, I'm going to say, if I subtract from it lambda times matrix I, and then take the determinant of that and equate it to 0 and solve, I would get the value of lambdas, which are the eigenvalues. Say, what? Yeah, it's not hard to prove it mathematically, but it's beyond the scope of this course. It's just you want to find a matrix such that when you multiply this matrix by the vector, you get the same direction. How do we talk about that? Meaning, I multiply the vector by constant. Notice if I multiply this by 3, I get 6, 6. If I multiply it by -2, I get -4, -4. All the time, I didn't change the direction. So there must exist a number or few numbers that if I multiply them by the vector, it doesn't change. It doesn't change. They multiply a matrix that if I multiply it by the vector, it stays in its direction. And the way to find it is using that. Here is B. We know that B is a 2 by 2, so I2 is 1, 0, 0, 1. Lambda times I would be lambda 0, 0, lambda. And when I subtract this from that, we learn how to do the subtraction before. We say 3 minus lambda. -1 minus 0 is -1. 2 minus 0 is 2. And 4 minus lambda is 4 minus lambda. And then I'm going to equate that to 0. How do I find the determinant of a 2 by 2 matrix? Simple, very simple. Let's look at this one. For example, suppose I want to find the determinant of B. The way I teach my students, especially in the beginning so that they don't make errors, is to open, and you might have seen that when we did the 3 by 3 using the duplicate column method. I'm going to multiply the main diagonal elements, 3 times 4, write it here, and then subtract the other diagonal. 2 times -1 is -2. Notice negative times negative is positive, so that would be 14. So you don't get confused with negative times negative. That's why I prefer to put each one in its own pair of parentheses with a negative sign between them. So we are going to do something similar. I'm going to multiply this by that and then subtract -1 times 2. So when you multiply 3 minus lambda times 4 minus lambda, it's the same as lambda minus 4 times lambda minus 3. Do you see that? I think we mentioned that before. It doesn't matter. So basically, you will end up with lambda square minus 7 lambda plus 12 minus -2, so plus 2 equals 0. Okay, so really this is, you will not end up with an integer number. So because we were making these numbers haphazardly, let's repeat that with a better example. Let's say, in fact, I can pick numbers that would make sense. For matrix A is 2, 2, 1, 3. Okay, I know that would work. Maybe we'll talk about that later. So now if I do A minus lambda I will get the determinant of 2 minus lambda, 2, 1, 3 minus lambda, right? And equate that to 0. So when I multiply, I will get lambda square minus 5 lambda plus 6 minus 2, right? This minus that. And equate that to 0. So that would be lambda square minus 5 lambda plus 4 equals 0. And that's a quadratic equation. You can factor it. So you get lambda minus 4 times lambda minus 1 equals 0. So either lambda equals 4 or lambda equals 1. These are called what? Yes, these are called the eigenvalues. Yes, these are the eigenvalues. For each eigenvalue, there corresponds an eigenvector. Say, wait a second, what does that even mean? Okay, let's pick the first one, which is 4, and then substitute it back. So for lambda equals 4, I will get a matrix that is 2 minus 4, -2 and 2, and then 1 and 3 minus 4 is -1. Do you see that the two rows are like copies, not copies, but multiples of each other? We want to solve this equation that when I multiply that by x1, x2, for example, let's call them that, I get 0, 0. If you remember clearly how we did it in Gauss-Jordan, you would realize that there would be infinite solutions for that because I didn't really give you two equations. I tricked you and I give you only one. And then I multiply that one by -1/2 and I give it back to you. So whether you solve the top or the bottom, you will get the same result. Yes, because remember, I can stretch the vector 2 and 2 by any factor, or I can squeeze it or shrink it by any factor. So there are infinite number of solutions. And you say, so which one do I pick? No, wait a second and you will see it. Now, when I write that, I would say negative 2x1 plus 2x2 equals 0. And then x1 minus x2 equals 0 also, which is the same thing. Meaning if I move 1 to the other side, I get 2x1 equals 2x2 or x1 equals x2. So give me a vector. Give me a vector that has x1 equals x2. So the easiest one is 1 and 1. Someone can say, oh, I'm going to use negative 13 and negative 13. Yeah, be my guest. It's the same thing. Okay? It's the same thing. Okay. Now, if I take this matrix and multiply it by 1, 1, do you see what will happen? I will get a new vector. 2 times 1 plus 2 times 1 is 4. 1 times 1 plus 3 times 1 is also 4. So I get 4, 4. Notice, this is 1, 1. But when I multiply this matrix by it, I got the same vector again. Okay. Let's go back and say for lambda equals 1. If I substitute, I get 2 minus 1 is 1, and then 2, and then 1, and then 3 minus 1 is 2. So I get the same exact equation, x1, x2 equals 0, 0. So x1 plus 2x2 equals 0, meaning x1 equals negative 2x2. So that's how do I make a vector such that x1 equals negative 2x2? I can pick any numbers. The easiest is to make x2 equals 1, right? And then multiply 1 by negative 2, so you get negative 2, 1. Okay? Okay. So, what did I want to say? Notice that if I multiply this matrix by that matrix, 2 times negative 2 is negative 4, and 2 times 1 is 2, so I get negative 2. And if I multiply 1 times that, you get negative 2, plus 3 is 1. So you get the same matrix, the same vector again. Okay, so now I found 4 and 1 are the eigennumbers or eigenvalues, and these two guys are the corresponding eigenvectors. Now I want to show you something interesting. If I write in the middle the eigenvalues as they are, notice I have a lambda and lambda. I subtracted lambda times I, remember? Lambda times lambda, lambda, 0, 0. So I'm going to write them in that form. 4, 1, 0, 0. Lambda 1, lambda 2. Now, what was the corresponding matrix vector of eigenvector of 4? It was 1, 1. So I start with 1, 1. What was it in the second column that I have 1? It was negative 2, 1. Negative 2, 1. If I can find the inverse of that and multiply it here, I know it looks so confusing, but really the way to find the inverse of a 2 by 2 matrix is very easy. All what you have to do is first to find the determinant, which is 1 minus negative 2 or 3. Okay? Switch the elements on the main diagonal, but they are the same. But I switch them. The 1, 1 become 1, 1. And then the other diagonal, you leave it as it is, but change its sign. The negative 2 becomes 2, the 1 becomes negative 1. So this guy becomes 1/3, 2/3, negative 1/3, 1/3. Bear with me for a second. I want to multiply these three matrices simultaneously. Like, first I can multiply these two first and then multiply the result by that, or multiply these two first and pre-multiply by that. It doesn't matter. So that becomes We have to do it on 2 steps. The second one is still that. But the first one I get 4 plus 0 is 4. 0 plus -2 is -2. 4 plus 0 is 4. 0 plus 1 is 1. You see, it didn't take much time. And then I'm going to multiply these two together. 4/3 plus 2/3 is 6/3 or 2. 8/3 minus 2/3 is 6/3 or 2. 4/3 minus 1/3 is 3/3 or 1. 8/3 plus 1/3 is 9/3 or 3. What? I got back my matrix. And you say, am I doing all of that so that I multiply 3 matrices and get back my original matrix? Are you out of your mind? I say, no, I didn't do it for this reason. So why did you do it? I say because dealing with this matrix is fascinating. Suppose I want to find a square or a cube or a to the 5th power. Notice if I want to solve a to the 5th power, I'm going to multiply this matrix by itself to get a square, and then multiply it by itself again to get a cube, and then multiply it again, and then multiply it again. Here, how do I do it? I say a to the 5th equals. I leave the first matrix as it is. I leave the last matrix as it is. And I look at the eigenvalues and I raise them to the power of 5. 0 stays 0, 1 to the 5th is 1, 0 stays 0, 4 to the 5th is 2 to the 10th, which if you done any computer, you know it's 1024. Now, if I multiply these 3 matrices, I will get a to the 5th, which is less cumbersome than to do that. In fact, there are many operations you can do on this matrix, but it's always, let's use a calculator. It may take some time. I'm going to pick a matrix. So let's go to matrices and define 3 matrices. The first, all of them are 2 by 2. The first one is 1, -2. Let me move it here. 1, 1. The second one, so let's quit, go back, edit. The second one is a 2 by 2. It's 1024, 0, 0, 1. And then I'm going to go back, make that a 2 by 2, 1/3, 2/3, -1/3, 1/3. Now I'm going to multiply them. So I'm going to say matrix A times matrix B. I don't know if the calculator, I never tried it. I should have tried it. Would it multiply all 3 together, or do I have to use? No, I don't think so. No, it did. It gave me this matrix. Now, let me go back to my original matrix. So let's say matrix D, I'm going to enter these numbers in it. That's a 2 by 2, yes. But I'm going to enter 2, 2, 1, 3. Okay, now I want to get matrix D and raise it to the 5th power. Let's see if we get that. Do you see what we had? The same exact thing. In fact, some people can give you a matrix like that and tell you, can you find e to the matrix A? And you say, what? Can I raise e to the matrix A? Yes. You would see e to the fourth, e to the first, and then multiply the matrices and get a result. You can take the square root of a matrix, which when square root of a matrix would be 2, 1, right? Do you see that? If I change the four, so if I go to matrix B and change it, instead of being no, not matrix A, I'm sorry, matrix B. I forgot to go down one. Which was that? I can make it 4 and 1. So I make it 2 and 1, I'm sorry. 2, 0, 0, 1. Okay. No, this is 0 and this is 1, so it's okay. Now, if I multiply, the square root of that is 2 and 1, right? So I'm going to multiply A times B times C. I changed B and I made it 2, 1. So now I'm going to say, I don't have to do that. I can go back. And now I say multiply A by B by C, right? Because now I change B. I change B. So I get this matrix, 4/3, 1/3, 2/3, and 4/3. No, 5/3. 1 and 2/3, 5/3. Now, what if I multiply this matrix by itself? So I should have, okay, let's go back one last time. I'm going to make matrix E a 2 by 2. And then I'm going to say 4/3, 2/3, 1/3, and 5/3. This is the matrix we found. Let's square that and see if I get my original matrix. Okay, second matrix, E square, 2, 2, 1, 3. So I could find the square root or the cube root or anything about this matrix, which it was pretty much impossible because how can you find a matrix that if I multiply it by itself, I get 2, 2, 1, 3? How? Without this method, you couldn't. And that's the power or one of the powers of the eigenvalues and the eigenvectors. I know it was maybe too much to cram in one session, but I hope you understood what we were saying, that the eigenvalues are specific numbers that if you multiply the corresponding matrix by, they don't change direction. They stay in place. You are just extending or shrinking them. And then using this approach, expressing the matrix like that, I can keep the first and third and apply whatever I want to the middle one. I can find any squares, any roots. Some people would be as crazy as to, as I said, e to the x, e to the power of a, e to the matrix a, and there are applications in engineering and science for those and stuff like that. And basically, I think this is very interesting if you understand what the eigenvalues do and how to create the corresponding eigenvectors. I hope you enjoyed it. And if you have any questions, please leave them in the comments section, and I will get back to you as soon as I can. Thanks and have a great day. Bye.